Jai Hind students. Now we are going to discuss the next complex topic of this analog and digital communication subject, and that is angle modulation. So first we start with what is angle modulation. Actually, modulation is the process in which we are superimposing the message signal on the carrier signal and we are getting a modulated signal that is having a high frequency that can travel to the long distance, because due to the high frequency its power is increased and the signal can travel to the long distance, and also it will make get better immunity for the noise interferences. So in that part, first of all, in the angle modulation we are taking a message signal. That message signal is equal to mt is equal to am cos omega mt. Similarly, for modulation of this we are getting a carrier signal, and that carrier is AC cos omega ct. So now, to define this, we can easily understand here one point, that in this particular part you can see here that this is the message and this is the carrier. As per the definition of the angle modulation, we are going to change the angle part of this carrier signal as per the instantaneous value of the message signal. And this angle is actually having two information. First one is frequency and second one is phase. So at one time, either we are changing the frequency of the carrier or changing the phase of the carrier as per the instantaneous value of the message signal. And at that time, when frequency is going to be changed, the amplitude and phase of the carrier will be kept constant. So by this process we will get two types of angle modulation, and that types are FM and PM. FM stand for the frequency modulation, whether PM stand for the phase modulation. So how this process is going to be done? So here, to understand this point, we will discuss all the points one by one. Here you can see that in the FM part, when we are going to change the frequency of this carrier, then that will automatically change this actually angle part of the signal, and we will get the resultant angle modulated signal by AC cos phi I. Means that angle is going to be changed as per the modulation. Now that phi I is basically defined by the d phi upon dt is equal to omega. You know that the angular frequency is ratio of angular displacement by time. So by this process we can get the d phi I upon dt, and that is omega I, because when we are doing the frequency modulation, then the actual frequency omega c of the carrier will change as per the message signal, and we will get a instantaneous frequency that is denoted by omega I, and that value is actually omega c plus kf mt. That is the value of instantaneous frequency. How we are getting this? This instantaneous frequency is going to be get by changing the carrier frequency. The carrier frequency is omega c, and that carrier frequency is going to be changed as per the instantaneous value of the message, and the instantaneous value is mt message, and its value is defined by in the proportional with the kf, where kf is the frequency sensitivity that denote how much frequency going to be changed as per the message value. So the instantaneous value omega I we will get, and that omega I denoted by this. So to calculate the phi I here, by this equation we will get phi I is equal to integration omega I dt. So if we put this equation here, we will get this angle modulated equation. So as per this system, you can understand here, angle modulation has two forms. First one is frequency modulation. That message is represented as the variation of the instantaneous frequency of the carrier, and the phase modulation, where message is represented as the variation of the instantaneous phase of the carrier. So you can here see that the same equation AC cos phi it, where phi I is equal to fit is equal to 1 upon 2 pi d phi it upon dt, because that omega is the 2 pi f, means omega I is equal to fi. So that st is equal to a cos 2 pi fct plus phi t, और तो phi t की वैल्यू जब हम यहाँ पे पुट कर रहे हैं, then we are taking these two equations. So here you can see that in the frequency modulation, what we are going to do, we are going to put that value 2 pi fct plus 2 pi kf m tau d tau, because we are taking the integration as per the first discussion. So kf is the frequency sensitivity, and instantaneous frequency is equal to fit is equal to fc plus kfmt. Assume zero initial phase. So angle phi it is equal to 2 pi 0 to t fi tau d tau, and fc 2 pi fct plus 2 pi kf integration 0 to t m tau d tau. This is the resultant fm wave. So this is the frequency modulation part. Means in this first discussion, when we are discussing this part, when we are changing the frequency, we will get this phi I. But when we are talking about the phase part, what will happen? You can see here in the phase modulation, actually now directly we are getting this phi I by omega ct plus kp mt. Now the phase means angle part of the signal is going to be changed. That's why we will get this part. So now here no integration is required. We are directly going to put this part into the AC cos phi I, and by getting this we are getting this 2 pi fct plus kp mt, where omega c is the 2 pi fc and kp mt is the part where phi t is equal to kp mt, and kp is the phase sensitivity. Similarly, as for the discussion last one was the frequency sensitivity. So the instantaneous frequency here is fc is equal to kp by dmt dt 2 pi. So these are the two parts, that phase modulation and second one is frequency modulation. So when we discuss or compare these two parts, here you can easily understand one point. In frequency modulation, actually we are taking the integral part of the message signal, whether in the phase modulation we are directly taking the empty signal. Here you can see that this is the integral part, whether in this phase there is no integration. So here we get a relationship between FM and PM. That relationship shows that we can get the frequency modulated signal by using a phase modulator, or we can get a phase modulated signal by using a frequency modulator. How it is possible? Because you can understand here one point. This is a phase modulator. This phase modulator actually give us the value with kp mt, means no integration part, and here input is mt. But if we apply the integration on this mt, we will get mt dt, and if we apply this signal to this phase modulation, what we will get, that is kp integration mt dt, that is equivalent to FM signal. So here you can see that by using a phase modulator and a differentiator, we can get the frequency modulated signal by a phase modulator. Similarly, in the case of FM, we are having a frequency modulator, and that frequency modulator is actually generating the MT DT. But when we are providing that MT, first we differentiate this and we will get the DMT by DT, and by putting this here we will get DMT DT DT and get MT. So it will give us the phase modulated signal. Means you can easily generate phase modulated signal by using a frequency modulator or vice versa. So by discussing these points and the basic discussion of the FM, we can easily understand that FM having some basics, that FM signal where we are using for the high fidelity broadcast, that is for the very high frequency signals, that is from 30 megahertz to 300 megahertz. Also wideband FM, actually FM is of two kinds, and that are narrowband FM and wideband FM. This narrowband and wideband FM is defined by the value of KF, means frequency sensitivity. If frequency sensitivity value is quite high than the 1, then we will get the wideband, but when KF value is very less than 1, we will get the narrowband FM. So this is the differentiation between wideband and narrowband FM. So wideband FM is used for the FM TV, narrowband FM is used for the two-way radios. Similarly, in 1933, FM and angle modulation proposed by Armstrong but succeeded in 1949. Also, this will provide the base for the digital frequency shift keying, phase shift keying techniques. Also, AM and FM having the transfer waves and longitudinal wave respectively. So these are the FM basics. Also, when we are discussing this angle modulation, it is required that we will compare this with the amplitude modulation. So here you can see that in the amplitude modulation, that is linear, it means it just moved to new frequency band, spectrum shape does not change, no new frequency generated. But in the angle modulation, this is non-linear and spectrum shape does change and new frequency generated. In the wideband, there are number of sidebands, that is equal to n. As soon as the frequency sensitivity or modulation index of frequency modulation increases, the number of sideband also increases. So that's why the new frequency generated. Similarly, in the amplitude modulation, there are translated version of MF, and bandwidth is less than twice or 2 omega. Whether in the bandwidth is much larger than the 2 omega in the case of angle modulation, because in the angle modulation, when we want to find out the bandwidth, we will use the Carson's rule. And as per the Carson's rule, the bandwidth of narrowband FM is equal to AM, means twice of FM. But when we are talking about the wideband FM, it is quite larger than the 2 FM or 2 omega. So this is the basic description of or basic comparison of angle modulation and amplitude modulation. Similarly, there are some pros and cons that why we need this angle modulation. For the better noise reduction and improved system fidelity, we will actually use this angle modulation, because whenever this noise is going to interfere with the actual signal, what will happen? Actually, if this is the signal, let us take this signal. If noise is going to added here, then what will happen? That noise will be added only at the amplitude level of the signal. Or if this is the signal, then how noise will going to affect this? This is the noisy signal. So when we are talking about the angle modulation, this amplitude is not going to change. that is going to be same throughout the system. By this diagram you can here see that this is the carrier, this green part is denoting the carrier, whether this red line is showing the signal, and when we are getting the output, this is the frequency modulated output of this signal. Here you can see that amplitude value is same, you can see here the phase is same, but you can see here the number of cycles as per the signal is changing, means some here that frequency is low and somewhere this frequency is high. So by this you can understand this point. So here you can understand that point, that how better noise reduction is going to be achieved. Also disadvantage, low bandwidth efficiency, because bandwidth requirement is quite high, that's why bandwidth efficiency is quite low. Also the implementation of the FM is also complex, very complex. And one point is also that FM broadcasting range is quite low compared to the AM. So when we are talking about the FM radio broadcast, that is for a limited region or limited radius, but when we are talking about the AM, that range is quite high. So basically the application of, as per that part, FM applications are FM radio broadcast, TV sound signal, two-way mobile communication, cellular radio, microwave and satellite communication. So these all are the different kind of angle modulation applications which we discussed already. So this is all about the angle modulation, and here one point is very important, that is related to the frequency deviation. So what is that frequency deviation? Actually I am again and again talking one point, that my carrier frequency is actually FC, and that carrier frequency actually FC is going to be changed again and again. And how it is going to be changed? You can see here that one point, that whether this frequency is going to be increase or decrease, but that increment is decrement is fixed with the value of some deviation value, and that deviation value is actually the value which is denoted by here by del f, and that del f is equal to kf am. Kf is the frequency sensitivity, whether am is the maximum amplitude of the message signal. When we multiply both of them, we will get the frequency deviation value, and that frequency deviation value give us the value of FM signal, which is denoted by how, that FC plus del f or FC minus del f. So as discussed earlier, there are two kind of frequency modulation. One is narrow band, whether another one is wide band. In a narrow band, we are actually having these two parts only. But as soon as the KF value will increase further, means higher value, then that FC plus del f converted into FC plus 2 del f, FC plus 3 del f, and these all part are denoting the increasing number of sideband in the FM signal. So this is all about the frequency deviation part. Now similarly, again the same discussion which we discussed earlier in the amplitude modulation also, that in amplitude modulation we defined the modulation index for AM, and that modulation index of AM is going to be help as how much modulation is going to take place. Similarly in the FM we are using the again modulation index for the FM, and it indicate by how much the modulated variable instantaneous frequency varies around its unmodulated level message frequency. And the value of this modulation index for AM, I already told you, that was MA is equal to VM by VC, whether in the for frequency that is beta or MF, and that is denoted by deviation divided by message frequency, and the deviation is maximum value of KFMT. So you can easily understand here that the modulation index in both the cases is somehow related to the variation. means how much variation is there in that particular parameter, whether it is amplitude or that is frequency. As per that ratio, we will decide the modulation index for AM or FM, and the bandwidth is can be find out by this equation, that is AT is equal to minus infinite to T M alpha D alpha. So this is the modulation index part. So that is about the brief introduction of the FM or the frequency modulation or angle modulation. So in the next lecture we will discuss about the another topic. So Jai Hind, thank you.